In this video, we will talk about point estimates. Suppose we are given a population. Associated to this population, a parameter would be a population characteristic that we are interested in studying. This is something that remains fixed once the population is fixed. A statistic is a quantity that is calculated from a random sample coming from a population distribution. So a statistic by itself is a random variable, which means that it will change as the sample data changes. A general goal is to use statistics to make inference about population parameters using random samples. To begin, let data be a population parameter. A point estimator for data, which will be denoted by data check, is a statistic which, when evaluated on sample data, gives or estimates a sensible value for the parameter data. It is important to note that there can be multiple estimators for a given parameter for the population. The goal or the difficulty then is to find conditions that would help us select the best estimator for data from a given choices that we might have available at our disposal. And to that end, we will begin our study by studying unbiased estimators. So let data be a population parameter that we are interested in studying, and let data check be an estimator for data. Remember that data check is a random variable. We want to define the bias of data as the difference between the expected value of our random variable data check and the true value of the population parameter, that is data. In other words, the bias of data check is going to be the expected value of data check minus data. This leads us to our first important definition. We will say that data check is an unbiased estimator for data if the bias, that is the expected value of data check minus data, equals 0 for every possible value of the population parameter data. Let's work out some examples to get a hang for what's going on here. So let mu be the population mean and sigma squared the population variance. And let x1, x2, all the way up to xn be a collection of IID random variables, that is a random sample. Recall that the sample mean is defined as the sum of all the xi's divided by n, and it satisfies the property that the expected value equals mu, which tells us that if our parameter of choice was the population mean and our estimator was the sample mean, then the expected value of the sample mean equals the population parameter for all choices of population parameter. This means that the sample mean is an unbiased estimator for the population mean mu. We can work out another example of an estimator for mu. Let's define data check to be x bar minus 5. In this scenario, a simple calculation shows that the bias of the estimator is going to be the expected value of x bar minus 5 minus mu, which equals minus 5. A non-zero number, which lets us conclude that data check is not an unbiased estimator for the population mean. Notice that even though in this scenario we will have the expected value of theta minus theta check to equal 0 if the population mean was 5, right? So the condition that the bias has to be equal to 0 for all choices of theta is important. Let's move on to another example. Let y be the sum of the squared deviations of each of the sample entries from its sample mean. Then we can show that the expected value of y is in fact going to be n minus 1 times the variance, that is sigma squared, which means that the expected value of 1 over n minus 1 times y is going to be sigma squared. So we can define the sample variance to be 1 over n minus 1 times the sum of the squared deviations. And this, as we have shown above, is going to be an unbiased estimator for the population variance sigma squared. For our final example, we are going to consider the estimator data check that is going to be defined by 1 over n times the sum of the squared deviations of the sample entries from the sample mean. This is going to be equal to 1 over n times y, where y was defined in example 3. A simple calculation then shows that the expected value of data check is going to be equal to n minus 1 divided by n times the population variance sigma squared. As a result, the bias of data check, if data were the population variance, ends up being minus sigma squared over n. This calculation shows that data check is going to be a biased estimator for the population variance sigma squared. However, notice that since sigma squared is fixed and the sample size can be as large as we want, we can control the bias of this estimator to be as small as we want by choosing a very large sample to work with. We are hence led to the principle of unbiased estimation, which states that when choosing among several different estimators for a population parameter data, we want to choose one that is unbiased. While it is desirable to have an unbiased estimator, it's also important to note that it is possible to have several unbiased estimators for a given population parameter data. So the problem now becomes, how do we choose from among these different unbiased estimators? To answer that question, we are led to describing the variance of an estimator. So suppose theta 1 and theta 2 are two unbiased estimators for a given parameter theta. This means that the expected value of theta 1 check and theta 2 check both equals to theta. So the question now is, what do we choose, theta 1 or theta 2? And the answer really depends on how the values of theta 1 check and theta 2 check vary about the expected value, that is theta. That is, we are really looking to understand the variance of an estimator. So recall that an estimator is a random variable, and the variance of the estimator is just going to be the expected value of the squared deviations of the estimator from its expected value, that is theta. So this number measures the variation of the estimator data check about its expected value, that is theta. And since we would want these values to be close to their expected value, we would ideally want the variation of data check to be as small as possible. This leads us to the second important principle, that is the principle of minimum variance unbiased estimation, which says that among all unbiased estimators, we would want to choose an estimator for theta that has the least variance. If such an estimator data check exists, it will be called the minimum variance unbiased estimator, or MVUE for data. We finish up with two important notes. Given a parameter theta for the population, it is usually desirable to choose a minimum variance unbiased estimator to estimate data. However, depending on the context, it is possible or even useful to choose a biased estimator uh, with a smaller variance. So these are context driven decisions. Just to have a pictorial view of what is happening, look at the following two pictures. The picture on the left is an example where we have two unbiased estimators, and the variance for the blue estimator is less than the variance of the red estimator. So we would want to choose the blue estimator as our estimator of choice if we were to choose between these two estimators. Note that the blue estimator might not necessarily be the minimum variance unbiased estimator. For the picture on the right, the red graph corresponds to the minimum variance unbiased estimator, data 1 check. But notice that data 2 check, which is the blue graph, is a biased estimator but has a much smaller variance. And depending on the context, it might be useful to use that estimator over data 1 check. So, to briefly summarize, we spoke about unbiased estimators and the variance of the estimator. Uh, we will talk more about estimation in future classes. This is all for now. Take care, and I will see you around.